All right, silly people, here's the situation. We're essentially going to be taking a derivative numerically of a function that we're going to define. It's going to be e to the 2z. But the method of doing the derivative is actually by using a identity from the Cauchy derivative formula, which is contour integral stuff. So um, really tough, complex integrals. And the theory is really interesting to read, and I recommend that you read it by yourself. Um, but I'm just going to do the part of the problem that is actually writing the code which does the thing. That's pretty usual. So that is going to, I'm going to create a code cell here. We are going to need the CMath version of the exponent function, and we're going to use the factorial function from math. We don't even need numpy here, I don't think. So let's just go ahead and grab those from math import factorial. And also I'm going to grab pi because there's pi's in a lot of these parts of the problem. Also import cmath as seam. So first of all, we're going to define the function that we're taking the derivative of, f of z, which is going to be returning cmath exponent 2 times z, pretty simply. We're going to do this for n equals 10,000, as according to the problem statement. And we're basically going to create a for loop for n in range 1 to 21, because we're going to print out the first 20 derivatives of this function, right? And in here, we're going to create a sum, which is going to start with value equals 0, because this formula involves a sum over k, so k in range. This one just goes to n. And in here, it's the sum of f of zk. What is zk? It turns out to be e to the I to pi k over n for each of these. So let's do zk equals cmath.exp 2j times pi times k divided by n. I think that was everything in the formula. Yeah. And then you add onto the sum f of zk times, it's another exponent, cmath.exp minus 2j times pi times k times m over n, I think. Yeah, this one involves an m in there as well. So, okay. Now that we have the sum, we can have it print out the value of the derivative as being the factorial of m times the sum divided by n. And we should get the first 20 derivatives of e to the 2z evaluated at z equals 0. And what we have right now is actually, since all of these are complex numbers, the whole complex number for each of those. So let's just get the absolute value of that, shall we? That's all that matters, really, is the absolute value. So it's printing out, as Newman predicted, what is about 2, 4, 8, 16, 32, 64. It's just the powers of 2, right? Because analytically, the derivatives of e to the 2z at z equals 0 are just that. Just powers of 2 depending on how many derivatives you do. So we got some sensible answers there. All right.